So I want to start with a pretty provocative question.
Oh, here we go. Lay it on me.
What if?
Mm.
What if meaning isn't something that lives inside your own mind?
Okay, so not in the individual. Where then?
What if it actually lives in the chatter between minds?
That is a very provocative way to open the floor. You're coming out swinging today.
Well, I try, but seriously, think about it. For centuries, we've had this default assumption that the mind is an isolated island.
A container. A little box full of thoughts and symbols.
Exactly. I sit in my ivory tower, I look at an object, I assign it a name, I see a spoon, I call it a spoon, and that's the end of the story.
But you're suggesting that whole model is just wrong.
Completely wrong. What if the mind is actually more like a single node in a vast planetary network?
That's a huge paradigm shift. You're basically taking the brain from being a standalone PC, disconnected from the Wi-Fi,
Just churning away on its own hard drive.
and turning it into a terminal
Mhm.
logged into a massive distributed system.
Exactly. And today, we're going to explore a really wild idea, which is that gossip, yes, gossip, the stuff we usually dismiss as trivial,
Or even malicious.
right, that it isn't just idle talk. It might actually be the essential protocol that grounds our entire shared reality.
It's the killer app of human evolution. I love that framing. Without gossip, you don't get civilization.
And you arguably don't get meaning as we know it.
It's the software that runs the whole network.
We have a pretty massive roadmap ahead of us today. We are going to connect some dots that, let's just say they don't usually get connected in the same room.
I'm intrigued.
We're talking Ludwig Wittgenstein's philosophy of language,
Okay, heavy stuff.
combined with Robin Dunbar's evolutionary anthropology, and get this distributed computing gossip protocols.
Which, and this is the surprising part, is actually going to help us understand why an isolated brain is structurally, incapable of developing meaning on its own.
We're going to look at the math, the biology, and the code.
It's the full stack.
Welcome to the Deep Dive. I'm Satosha.
And I'm Satoshi.
Before we jump into that deep end, I have a huge milestone to share with you.
Oh, this is good news.
We just crossed 1,000 hours of listening time on YouTube.
That is incredible. A huge, huge thank you to everyone tuning in and sticking with us through these pretty dense topics.
It really is amazing. We call this the deep dives, but internally we kind of think of it as the experiment.
Right.
We wanted to test if there was an appetite for academically rigorous research outside of its usual home, the philosopher's den.
And it turns out there is.
You guys have proven there is. There's a real hunger for deeper conversation beyond the headlines, which are, well, let's just say it.
They're an attention grab.
They are. But on that note, we do have a favor to ask. We need to hit 1,000 subscribers on YouTube to unlock the funding we need for the Mosaic AI video editor.
Mosaic. For anyone who doesn't know, this is a tool a lot of creators are looking at right now. It helps turn audio-heavy shows like ours into more of a visual experience.
It does automatic infographics, cinematic captions, that kind of thing.
It would let us actually visualize some of these really complex ideas we talk about.
It would take the show to a whole new level. And let's be fair, we aren't the only ones asking for Mosaic, but I think our kind of content is just perfectly suited for it.
It really is.
So if you're digging these conversations, please hit subscribe on YouTube, YouTube Music, Apple, Spotify, Fountain.fm.
Wherever you're listening, it makes a huge difference.
It helps us keep the lights on and the research coming.
Absolutely. So now, set the stage for us. Where did this specific topic even come from?
Okay, so about a month ago, we did a deep dive called Meaning of Meaning. You might remember we had that kind of wild artwork with Keanu Reeves and the Yogi Child bending a spoon.
Hard to forget that image. It was very The Matrix meets heavy metaphysics.
Right. Well, a listener sent in a question that just sent us down a complete rabbit hole.
A really deep one, I take it.
The deepest, the listener asked, does meaning really live in the brain? Or is it an emergent property of the group?
Wow, that's a great question.
And that simple question made us realize is that the brain, it isn't the whole computer. It's just a node. A node within a network of thousands, maybe millions, maybe billions of minds.
All working together.
So listen tight. This is a really good one.
It really is. And to answer that, listener, I think we have to start with this concept we're calling the social synapse.
The social synapse.
Yeah. The core thesis we're exploring today is it's a tough pill to swallow for individualists, but here it is. An isolated brain can perceive, but it cannot mean.
Okay. Can perceive, but cannot mean. Let's unpack that.
Let's do it.
And let's stick with the spoon example since we're already on the topic of spoon bending.
Perfect. So let's run a thought experiment. Imagine a brain floating in a void. Or, maybe easier, a person totally isolated from birth on a desert island.
Robinson Crusoe,
Yeah.
but with no prior experience of society.
Exactly. This isolated brain looks at a spoon. What does it actually see?
Well, it sees the shape, right?
Yeah.
The shininess, the curve.
Correct. It sees edges, curves, luminance, maybe a metallic texture. It's getting raw sensory data.
The photons are hitting the retina. The visual cortex is firing.
It sees a physical pattern. It's processing contrast and boundaries, all the low-level stuff.
Okay, so I see the object, but I don't call it a spoon.
Exactly. And here's the kicker.
Hmm.
In total isolation, there is absolutely no functional reason for that brain to assign the distinct symbol spoon to that pattern.
Why not?
Because you don't need it.
I can just pick it up and use it.
You can just pick it up and use it. You don't need to name it spoon to know you can scoop up water with it.
Right.
You're relying on what's called the sensory motor loop. The psychologist J.J. Gibson called this affordances.
Affordances.
You see the object, and you immediately perceive its graspability or its scoopability. You just use it. The actual concept of spoon, the word, the symbol, the category, that is a coordinate in a social consensus.
It's not baked into the atoms of the metal.
Not at all.
So if I'm alone on that island, I might grunt at it or just use it as a little shovel, but I don't need a dictionary definition for it.
You don't. And this brings up a really important distinction. The one between how a computer handles meaning versus how a biological brain does.
This is a great parallel. We always compare the brain to a computer, but on this specific point, they work in fundamentally different ways.
They're almost opposites. Think about conventional computation. It's centralized, it's sequential, and it's incredibly efficient.
Why?
Because the symbols are completely arbitrary. You can just tell a computer, okay, from now on, the binary string 00000 equals spoon.
And the computer just says, got it, 0000 is spoon. Doesn't care if it's a spoon, a cat, or a nuclear launch code.
It doesn't know, and it doesn't care. The symbol is totally decoupled from reality. And this leads us straight to that famous thought experiment.
The Chinese room.
Jean Searle's Chinese room argument.
I love this one. It's such a classic. It perfectly illustrates the point.
It really does. So imagine you're locked in a room. You don't speak or read a single word of Chinese.
I'm a total monolingual.
But inside the room with you, you have a massive rule book, a giant algorithm printed on reams of paper.
Okay.
And people outside the room slide slips of paper with Chinese characters under the door.
These are the questions.
Right. You pick up the slip, you look at the characters, and you find them in your giant rule book. And the rule book tells you which new characters to write down on a new slip of paper and slide back out.
So to the person on the outside, it looks like I'm having a fluent, intelligent conversation in Chinese.
Exactly. They ask, how are you? And you slide out the characters for, I'm fine, thank you. They ask, what do you think of the weather? And you slide out, it's a bit humid today.
But inside the room, do I understand any of it?
Not a single word. Do you know if it's raining or sunny outside?
No clue. Are just matching shapes. I'm a pattern matcher, not a thinker.
You possess the syntax, the rules, but you have zero semantics. Zero meaning.
An isolated brain, or a standard computer for that matter, is just like the person in the Chinese room.
It's a merry-go-round of syntax. Spoon is defined as utensil. Utensil is defined as tool, but you never, ever break out of that circle to actually touch the real world.
It's a closed loop. So our messy, wet biological brains had to solve this problem in a completely different way.
We couldn't just have a lookup table because there was no programmer to write the rule book for us.
Right.
No, biology is decentralized and, frankly, very inefficient. We have to ground every single concept in raw sensory experience.
And this is where we have to debunk a really common myth in neuroscience, right? The grandmother cell.
Oh, yeah, the grandmother cell fallacy. The idea that there's one single specific neuron in your brain that lights up when you see your grandmother and only when you see her.
Or a Jennifer Aniston neuron, which they supposedly found.
Right. If we actually operated that way, one neuron for one concept, we would run into a massive mathematical problem called the curse of dimensionality.
That sounds like the title of a sci-fi horror movie.
It's less. It's basically a mathematical horror story. The world is just too complex. If you needed a separate, dedicated neuron for every possible version of a spoon.
Spoon in sunlight, spoon in shadow, rusty spoon, bent spoon.
Your brain would need to be bigger than the planet, The number of possible combinations explodes. It's computationally intractable.
So instead, we use distributed representations.
Exactly. A concept isn't a single switch flipping on. It's a chorus of thousands of neurons firing together in a specific pattern.
Okay, that makes sense. But you said this distributed system comes with a massive cost.
A huge one. And this gets us into the math of cognitive load. This is the part of the research that really just blew my mind. Why does the brain reject that simple, efficient computational shortcut of just saying 0, 0, 0, 0 equals spoon?
I would guess it's for certainty. Or maybe for redundancy, so if one neuron dies, you don't forget what a spoon is.
It's deeper than that. It's about achieving logical mastery. Let's look at the numbers. Imagine a tiny, tiny universe with just two binary variables. Let's say, is it metal and is it concave?
Okay, metal and concave. So that gives you 4 possibilities.
Right, what are they?
You've got metal and concave, which would be like a spoon. Metal and concave. Not concave like a knife, not metal and concave, maybe a plastic ladle. And then neither, which could be a napkin.
4 states. Seems simple, right?
Yeah.
But to truly understand the relationships between those two variables, to think scientifically about them, you need to master all the logical operations that can connect them.
And that's more than just the 4 states.
Way more. It turns out, for just 2 binary variables, there are 16 distinct logical operations.
16. Wait, I can only think of like A and D, or R, and not.
That's where most of us stop. But to really reason, you need things like logical implication. If it is metal, then that implies it is strong. You need exclusion. It can be either metal or concave, but not both. You need non-implication. You need the cognitive machinery to process all 16 of these potential relationships simultaneously.
And this connects back to developmental psychology, doesn't it? To John Piaget.
It does, perfectly. Piaget's work showed that mastering these 16 binary propositional operations is the cognitive threshold between childlike concrete thought and adult formal operational cognition.
It's the difference between just seeing things happen and actually understanding cause and effect.
Exactly. A child might just see you bang a spoon and it bends. An adult understands if this object is metal, then bending it will cause a permanent change in its shape. But if it were plastic, it might snap.
That's a huge cognitive leap.
It is. But here's the catch. Maintaining that level of logical clarity, keeping all those concepts distinct, requires a massive metabolic investment.
And this brings us to this idea of negative information.
Yes.
Which sounds like forgetting things or maybe fake news.
No, it's actually the opposite. It's the energy you have to spend to not think of things.
To inhibit wrong answers.
Precisely. Think of it like a sculptor. The statue isn't just defined by the stone that's left. It's defined by all the stone that was chipped away. For every yes, your brain says, every time it correctly identifies spoon, it has to actively shout no to thousands of competitors.
Fork, knife, ladle, spatula, shovel, trowel.
It's like a room full of people all raising their hands with suggestions, and your brain has to run around telling every single person except one to put their hand down.
And that shouting down, that inhibition must be exhausting.
It scales quadratically. This is the scary math part. If you have 100 concepts, you need roughly 10,000 inhibitory connections to keep them all distinct from each other.
Okay, that's already a lot.
Now consider an adult vocabulary, say 40,000 words or concepts. You need millions upon millions of these inhibitory connections, all firing constantly.
And that's why the brain is such an energy hog.
That's the stat we always hear, right?
20% of the body's energy for 2% of the mass.
And a huge chunk of that energy is spent on this negative information processing. We are literally burning calories just to keep our concepts from bleeding into each other.
We pay this enormous price. Why?
Because this massive, expensive, inefficient architecture is the only thing that lets us interface with a messy, high-dimensional reality without crashing like a brittle computer.
A computer sees an undefined variable and it just stops. It throws an error.
The brain just guesses. It's robust.
Okay, so we've established how the brain is built to handle this complexity. But that brings us back to the big evolutionary why. Why did we start using symbols in the first place? If I can just use the spoon without naming it, why invent the word spoon?
This is the evolutionary driver, and the key word here is displacement.
Displacement.
The ability to refer to objects, events, or people that are not currently present.
Okay, that makes sense.
I don't need the word spoon to eat my soup if the spoon is right here in my hand, but I absolutely need the word spoon if I want to ask you to go into the other room and get me one.
Ah. So symbols aren't for thinking, They're for communication.
They are compressed information packets that are optimized for bandwidth-constrained social channels. You can't beam the image of a spoon from your mind to mine. You have to use a low-bandwidth channel, your voice.
And this is where we get into our primate roots and the work of Robin Dunbar.
It all starts with grooming.
Monkeys picking bugs off each other.
It's the original social glue. Physical grooming releases endorphins, it lowers the heart rate, it builds trust and coalitions. It's a physical way of saying, I have your back. Literally.
But it has a major flaw.
A hard limit. It is a one-on-one activity.
You can't groom two monkeys at once. I mean, you could try, but you wouldn't do a very good job.
Right, it's inefficient. And because of this, primates have what Dunbar calls a time budget limit. They can only maintain a social network of about 50 individuals.
Any more than that, and you run out of daylight.
Exactly. If you spend your entire day grooming to keep all your friends happy, you starve to death because you didn't have any time left to forage for food.
But humans, our groups got bigger. We blew past 50 and hit that famous Dunbar's number.
About 150. That seems to be the natural size for human communities. But to maintain a group of 150 with physical grooming,
It's impossible.
Dunbar calculated you'd have to spend 40% of your day just picking nits off each other. It's mathematically impossible. The society would collapse.
So we needed a hack, a social technology hack.
And that hack was language. Specifically, it was gossip. Dunbar argues that language evolved as a form of vocal grooming.
Vocal grooming. I love that image. I can groom you with my words while my hands are busy doing something else.
It solves two enormous problems at once. First, it's multicast. I can speak to 3 or 4 people at the same time, effectively grooming all of them simultaneously.
You can't do that with your hands.
And second, it's hands-free. I can gossip while we're foraging, while we're hunting, while we're carving a new spoon. It's far more efficient.
And this is where the killer app idea really comes in. Because gossip isn't just saying, hey, how are you? It's about reputation management.
This is the crucial leap for meaning. To gossip about someone who isn't there. Hey, did you hear what X did yesterday? You need names.
You need symbols.
You need to be able to refer to absent third parties. And crucially, you need to enforce social norms.
You have to police the free rider.
Exactly. If someone in the group takes more food than their share, the gossip network lights up. Agent X is a cheater, don't trust him. But this applies to words, too, and this is the really subtle part.
How so?
If I hold up a spoon and I call it a shovel, the gossip network corrects me.
He doesn't know the words. He's unreliable. Don't listen to his directions to the good berry patch.
Precisely. Gossip enforces semantic norms just as strictly as it enforces social norms.
So the reason we all agree that a spoon is a spoon is because if I insisted on calling it a shovel, I would be, in a micro way, socially ostracized.
You'd be out of sync with the protocol. You become a noisy node in the network, you're providing bad data, and the network will eventually learn to route around you or ignore you.
That is fascinating. So the social pressure to conform is what grounds the meaning of words.
It's the error correction mechanism.
And this transitions perfectly into the philosophy of the network mind.
Yeah.
We've got the biology, we've got the evolution. Now let's look at the hard logic of it.
Let's bring in Wittgenstein.
We mentioned him at the top. His private language argument is dense, but it fits here perfectly.
It's the philosophical bedrock for this whole theory. Wittgenstein proposed this great thought experiment. Imagine a man who decides to keep a diary of a private sensation.
Okay. Like a specific kind of tickle or pain that only he feels.
Exactly. And every time he has this specific sensation, he writes the letter S in his diary.
S for sensation.
Right. But here's the problem Wittgenstein poses. A week later, he has a sensation. How does he know if he's using S correctly?
Well, he'd remember what the sensation felt like.
Would he? Or would he just think he remembers it? In total isolation, with no external reference point, there is no difference between being right and seeming right.
Whatever seems right to him is right.
And if that's the case, then the whole concept of correctness dissolves into meaninglessness. Without a community to check his usage, to say, no, what you're calling S is actually what we call indigestion. The symbol S has no stable meaning at all.
It's just arbitrary ink on paper. Doesn't refer to anything consistently.
Wittgenstein's conclusion was that meaning has to be a public institution. It can't be a private mental event.
And the philosopher Hilary Putnam took this even further, right? With his twin Earth experiment.
Oh, this is the great sci-fi one.
2 identical Earths.
Yes.
Yeah.
You have Earth and you have twin Earth. On Earth, The clear liquid in rivers and lakes is HO. We call it water.
Okay.
On Twin Earth, there's a liquid that looks identical, tastes identical, feels identical, puts out fires. But its chemical formula is totally different. It's, say, XYZ.
And the people on Twin Earth also call it water.
They do. Now imagine two people who are molecule for molecule identical, Oscar on Earth and Oscar on Twin Earth. Their brains are in the exact same physical state. They both look at the clear liquid in a glass and say, that's water.
But they mean completely different things.
Exactly. When Oscar on Earth says water, he means HO. When twin Oscar says water, he means XYZ. Their internal mental subjective states are identical, but the meaning of their words is different.
Because the meaning is determined by the external environment.
Putnam's famous conclusion was, meanings just ain't in the head. They depend on the causal chain linking you to the world and to your speech community.
Meaning is external. Okay, so philosophy is great for these thought experiments, but we like to see this stuff in action.
We want empirical evidence.
You mentioned an experiment with robots called the Talking Heads. Now, this sounds like a band, but I assume it's actually science.
It's fantastic science from a researcher named Luke Steels. He set up these robotic agents. They were basically just cameras on pan-tilt heads.
So talking heads.
Literally. They had feature detectors, so they could see basic things like red, blue, square, triangle. But, and this is the key, they had no dictionary, no pre-programmed language.
They were blank slates.
Total blank slates. And he had them play what he called a language game.
How did it work?
One robot, the speaker, would look at a board full of different shapes and colors. It would pick one, say, a red triangle, and try to name it. If it didn't have a word for that object, it would just make up a random sound.
Like mokip.
Exactly. Mokep. The other robot, the listener, hears mokep and has to guess which object the speaker is looking at.
And then it gets feedback.
Right. If the listener correctly points to the red triangle, the speaker signals success, and both robots strengthen the association in their internal memory between the sound mokep and the features of a red triangle.
Positive reinforcement. Like training a dog with a treat.
And if the listener points to, say, a blue square, the speaker signals failure and points to the correct object. That's negative feedback. They both weaken the wrong associations.
So what happened over thousands of these interactions?
At first, it was total chaos. Every robot had its own private language. One called the red triangle mokep, another called it dada. It was a mess.
But over time,
very, very quickly, through this constant process of interaction and correction, through this gossip protocol, the group converged on a shared lexicon.
they all started to agree that mokep means red triangle.
And maybe Malav means blue square. A stable, shared language emerged from the bottom up.
And they did this with no central server, no God robot telling them the correct answers.
No central control at all. It was purely emergent. And here's the absolute key finding. When Steels ran the experiment but prevented the robots from talking to each other, their private languages diverged. They drifted further and further apart.
But when they were allowed to interact,
They converged. This is empirical proof that it's the social interaction, the feedback loop of the game that grounds the symbol. It stabilizes the raw physical perception into a shared, meaningful reality.
that is the social synapse right there in a lab. The robots were literally gossiping about shapes until they agreed on reality.
They were. And this leads us directly into the computer science parallel. We keep using this phrase, gossip protocol. Well, in computer science, there is literally an algorithm called the gossip protocol.
I've heard this mentioned in the context of things like blockchain or big distributed databases.
Yes, it's critical for any large-scale distributed system like Amazon's DynamoDB. Imagine you have a database that's spread across thousands of servers all over the world. Some are in Tokyo, some are in New York, some in London.
How do you make sure they all have the same up-to-date information without a central master list that would create a huge bottleneck?
You use a gossip protocol. It's basically peer-to-peer whispering.
So server A in Tokyo just randomly calls up server B in New York.
Essentially, server A says, hey, here's a summary of the data I have. So server B compares that to its own data and says, oh, looks like I'm missing that update, or actually I have newer info than you do. They swap state and synchronize.
And then server B gossips with server C, and it spreads through the network.
It spreads exponentially. The technical term for the process is anti-entropy. It actively fights against the natural tendency of the system to become disordered and inconsistent.
Anti-entropy, I love that. Fighting the chaos.
And the goal is what's called eventual consistency. No single server has the perfect truth at any given moment, but through billions of these local interactions, the entire network eventually converges on a stable, consistent state.
And that is exactly what the human brain network is doing.
We are all just nodes running a biological anti-entropy protocol to maintain a consistent definition of spoon or justice or reality itself.
Okay, but hold on. For the brain to actually function as a node in this massive network, it would need a very specific internal architecture, right?
Absolutely.
We couldn't just be standard hard drives or we'd crash every time there was a disagreement or conflicting information.
No, and this brings us all the way back to the brain structure we were talking about at the beginning, those massive, expensive, decentralized neural networks.
The brain uses what you called sparse distributed representations, or SDRs.
Right. So let's visualize this. An SDR is like a giant vector. Imagine a stadium with, say, 100,000 seats. That's your vector space.
Yeah.
Now, a dense representation would be like asking everyone in the stadium to stand up at once. It's not very informative. But in the brain, it's sparse. Only about 2% of the people, 2,000 neurons, stand up at any given time.
And the specific pattern of who is standing is what represents the concept.
Exactly. The pattern for spoon might be the people in sections 101, 205, and 412 standing up. The pattern for fork might be sections 101, 307, and 520.
So there can be overlap.
There can be overlap. Section 101 might represent is a utensil, but because the space is so enormous, the overall patterns are mathematically distinct. This is called orthogonalization.
A fancy word for keeping things separate so they don't get confused.
Right. In a 2D space, like a tabletop, if you put too many things on it, they just pile up and become a mess. But in a 100,000 dimensional space, you have a nearly infinite amount of room to keep concepts separate but also related.
And this vast space allows the brain to do some really cool tricks.
Yeah. It allows for what are called vector symbolic architectures, or VSAs. You can literally do a kind of math with these concepts. You can take the vector pattern for shape and bind it with the vector for round, then superimpose the vector for material bound with metal, and the result is the vector for spoon.
So the metabolic inefficiency we talked about, the fact that we have 86 billion neurons and use so much energy, that's not a bug, it's a feature.
It is the entire point. That massive cost is what buys you the geometric space you need to run the gossip protocol effectively.
It gives us error tolerance.
Exactly. If your brain was a dense, efficient computer chip, one flipped bit, one single error, and the whole system could crash. With SDRs, if you lose a few neurons, if a few people in the stadium sit down by mistake, the overall pattern is still recognizable.
That's robust. It's fuzzy.
It allows us to be eventually consistent with our peers, even if our own internal state isn't 100% perfect at any given moment.
This is a complete reframing of why our brains are so complex. I always thought of it as a processing requirement. I need to be smart to solve puzzles.
But it's actually a networking requirement.
It's the hardware spec needed to support a system that can interface with a messy reality and reach a shared consensus with other messy minds.
We are literally built to network.
Wow. Okay, so let's try to tie this all together. Let's walk it back. We started with the humble spoon.
A humble spoon.
An isolated brain can see it, can grasp it, can use it, but it can't mean it.
Because there's no utility in creating a symbol if there's no one to communicate with.
Right. So to solve the coordination problem, to get you to go into the other room and pass me the spoon, we invented symbols.
But symbols are inherently arbitrary. It could have been spoon or glub. It doesn't matter as long as we agree.
So we needed a mechanism to make sure we all agree, to stabilize the meaning.
And evolution gave us gossip. It was the killer app that scaled our social network from 50 to 150 and, as a side effect, gave us a way to police semantic norms.
You say spoon, not glub, or we won't trust you and you won't get any of the mammoth meat.
Basically. And to run this complex social software, this gossip protocol, our brains evolved this incredibly massive, high-dimensional, energy-sucking architecture.
That acts just like a node in a distributed database.
Ensuring that meaning isn't a private hallucination, but a shared, stable, and robust reality.
That is heavy. It really challenges our ego, doesn't it?
Yeah.
We like to think of ourselves as these independent, sovereign thinkers. I am the captain of my soul.
But in reality, our most private thoughts, the very concepts and words we use to think them, are essentially rented from the community.
We're just library card holders for the dictionary of our culture.
That's a good way to put it.
But this leaves me with a really big lingering question. If the meaning of a simple object like a spoon is a social construct, what about the big stuff?
What about truth?
What about justice?
And that is the philosophical cliffhanger, isn't it? If the meaning of justice is defined entirely by its topology in the social network, by how the group gossips about it, reinforces it, and punishes deviations from it.
Then justice doesn't exist in the physical world of atoms, like a spoon does. It exists only in the connectivity between us.
It's a consensus hallucination. A very useful one, hopefully, but a hallucination nonetheless.
And in our modern networked world, where the gossip is moving at the speed of fiber optics and algorithms are now joining the chat.
The definition of that reality might be shifting faster than our biological brains can possibly update.
Are we just nodes in a massive meaning-making machine that is starting to run on autopilot? That's a question for a sleepless night.
Indeed, and it forces us to ask who or what is controlling the protocol.
Look, this story is obviously still unfolding. We've thrown a lot at you today: Wittgenstein, robotics, anthropology, distributed computing. But we genuinely want to know what you think.
We are not the final authority here. We're just gossiping about the research that's out there.
Exactly. We're running the protocol with you right now. So if you're a philosopher, an anthropologist, a computer scientist, or just someone who stares at spoons and wonders why, share your analysis in the comments.
Are we being too optimistic about this network? Too critical of the isolated mind?
Jump in. Correct our anti-entropy. Help us all converge on a better understanding.
We're always looking for collaborators to review our content, so please reach out.
And please don't forget the mission. Help us hit that subscriber goal so we can get Mosaic AI and start to visualize some of this madness. We'll put a link in the description to that meaning episode if you missed it. It gives a really great foundation for what we talked about today.
It's definitely worth a listen to see where this all started.
Until next time, keep searching, keep the quest on,